What if I told you that the difference between a universe teeming with life and a dead, freezing void comes down to a single mathematical error of 120 zeros? Today, we are going to examine the most terrifying discrepancy in the history of theoretical physics. As scientists, we are trained to respect the margins of error. In the laboratory, a discrepancy of 1% is an annoyance. A deviation of 10% might prompt a complete recalibration of our instruments. But what do we do when the two most rigorously validated frameworks in the history of human knowledge produce a discrepancy so vast that the human mind literally cannot comprehend the scale of the error? We are looking at a mathematical chasm. On one side of this chasm is the value predicted by quantum mechanics. On the other side is the value measured by our most sophisticated astronomical instruments. The difference between these two numbers is a factor of 10 raised to the power of 120. That is a 1, followed by 120 zeros. To call this an error is a profound understatement. It is the single largest divergence between theoretical prediction and empirical reality ever recorded in the annals of science. And yet, this colossal mathematical anomaly is the exact reason you possess the biological capacity to process the words I am speaking right now. Let us examine the parameter at the heart of this crisis. We call it the cosmological constant. In the architecture of the cosmos, this single metric dictates the kinetic behavior of empty space. It is the invisible throttle controlling whether the fabric of space-time stretches outward or collapses inward. If you want to build a universe capable of sustaining complex structures, the cosmological constant is the ultimate master dial on your control board. And for decades, theoretical physics has been haunted by a singular, unresolved nightmare: the gap between what our equations say this dial should be set to and where it is actually set. Steven Weinberg, a mind brilliant enough to unify the electromagnetic and weak nuclear forces, famously classified this as the worst theoretical prediction ever formulated. To truly grasp the gravity of this situation from an analytical perspective, we must model the alternatives. Suppose we adjust the cosmological constant upward by a microscopic fraction. The localized gravity of emerging matter would be instantly overwhelmed. Space would expand with such violent kinetic energy following the Big Bang that hydrogen clouds would be shredded before they could ever coalesce. You would have no stellar ignition, no galactic formation, no planetary accretion. The universe would be a sterile, freezing void of isolated particles rushing away from each other into absolute darkness. Conversely, let us adjust the parameter downward by that same microscopic fraction. The outward momentum of the initial expansion would be swiftly counteracted by gravity. Within a geological blink of an eye, the entire cosmos would aggressively fold back in on itself, crushing all emerging matter back into a singularity of infinite density. In either scenario, the data yields the same result: zero complexity, zero chemistry, zero observers. For the majority of the 20th century, the scientific community bypassed this anomaly by assuming the value of the cosmological constant was simply absolute zero. It was mathematically elegant. Zero requires no complex justification. Albert Einstein had originally inserted this constant into his equations of general relativity in 1917 to keep his theoretical universe static, only to famously discard it as his greatest blunder when empirical observations proved the universe was expanding. For 70 years, zero was the consensus. But the cosmos has a habit of shattering our most elegant assumptions. In 1998, astrophysical data completely rewrote our understanding of cosmic dynamics. By utilizing distant supernovae as standard luminous markers, researchers discovered that the expansion of the universe was not decelerating under gravitational drag. It was accelerating. This acceleration implied that the cosmological constant was not zero. It possessed a positive value. But this value was so infinitesimally small that it had evaded decades of rigorous astronomical observation. It was a whisper of a number, just potent enough to gently push the universe apart over billions of years without ripping it to shreds. But this is precisely where our theoretical framework violently collides with empirical measurement. According to quantum field theory, the vacuum of space is not a sterile void. It is a hyperactive arena of quantum fluctuations, where virtual particles continuously manifest and annihilate on subatomic timescales. This incessant quantum static generates a calculable energy density. When we plug the energy of these vacuum fluctuations into Einstein's equations, the predicted cosmological constant is 10 to the power of 120 times larger than the gentle, life-permitting whisper we actually measure. We are forced to conclude one of two things. Either quantum field theory is generating an impossibly massive number that is miraculously canceled out by an unknown counterforce to a precision of 120 decimal places, or our foundational understanding of spacetime is missing a critical, undiscovered variable. But the cosmological constant is merely the first piece of empirical data in a much larger, much more disturbing pattern. As we comb through the fundamental constants of nature, we find that the universe operates on a razor's edge of precision across multiple independent axes. Consider the empirical data surrounding stellar nucleosynthesis. In 1953, a British astrophysicist named Fred Hoyle confronted a profound chemical paradox. Hoyle was a brilliant theoretician and a fiercely committed atheist. He built his career arguing that the cosmos was a self-sustaining system, requiring no external causal agent. But Hoyle was looking at the periodic table, specifically at carbon. Carbon is the foundational scaffolding of all known biology. To forge carbon, the universe relies on stellar cores, where extreme temperature and pressure force lighter elements to fuse. The pathway to carbon requires 3 helium nuclei to collide and bond in a sequence known as the triple alpha process. However, the mathematics of this fusion process presented a severe bottleneck. When 2 helium nuclei fuse, they create beryllium-8, an isotope so violently unstable that it decays in less than a 10 quadrillionth of a second. The probability of a third helium nucleus striking this fleeting beryllium-8 target before it disintegrates is statistically negligible. Based on standard physical models, stars should be utterly incompetent at manufacturing carbon, yet the universe is saturated with it. Every strand of DNA in your body is proof that the standard model was missing something. Hoyle, utilizing pure deductive reasoning, reverse-engineered the problem. He postulated that carbon-12 must possess a highly specific, undiscovered quantum resonance state, precisely at 7.65 million electron volts above its ground state. If this exact energy level existed, it would act as a quantum mechanical catalyst, amplifying the probability of the triple alpha process by orders of magnitude. Hoyle took his theoretical prediction to the nuclear physics laboratory at Caltech. The experimentalists were highly skeptical of an astronomer dictating nuclear energy states based on biological necessity. Nevertheless, they calibrated their instruments and ran the experiment. The data returned a flawless match. The resonance state existed exactly where Hoyle predicted it must. But it was the sheer microscopic precision of this resonance that shattered Hoyle's philosophical worldview. If the energy level were shifted by a mere fraction of a percent in either direction, stellar carbon production would instantly cease. The universe had threaded a subatomic needle. Hoyle famously conceded that the data suggested a super-intellect had monkeyed with the physics, chemistry, and biology of the universe. This pattern of hypercalibration is ubiquitous. If the strong nuclear force were a fraction stronger, stars would burn through their fuel exponentially faster, leaving no stable environment for planetary evolution. If the ratio between gravity and electromagnetism were altered by a degree undetectable in everyday physics, the universe would be completely barren. Even the asymmetry between matter and antimatter in the early moments of the Big Bang was calibrated to a ratio of exactly 1 extra matter particle for every billion antimatter particles. We are the biological residue of that mathematically perfect surplus. For decades, physicists relegated this fine-tuning problem to the macroscopic realm of stars and galaxies. But recent empirical studies have brought this cosmic hypercalibration directly into our own biology. In 2026, researchers at Queen Mary University of London analyzed the fundamental constants governing the viscosity of liquids. Viscosity is dictated by quantum mechanical interactions, which are fundamentally anchored to the Planck constant and the charge of the electron. The researchers modeled what would happen to liquid dynamics if these fundamental constants were slightly perturbed. The data revealed a terrifying biological boundary. If you shift the Planck constant or the electron charge by just a few percent, the physical properties of water drastically change. In a biological system, this means human blood would instantly become either too viscous to be pumped through the capillary networks or too thin to maintain the internal pressures necessary for organ function. The exact same mathematical parameters that dictate the expansion rate of the cosmos and the fusion cycles of distant stars are simultaneously calibrated to allow the specific fluid dynamics required for oxygen transport in your cellular tissue. The tuning is not just out there in the cosmic void. It is coursing through your veins at this exact millisecond. The empirical reality of this fine-tuning is no longer a subject of scientific debate. The tuning is an observed, measurable fact of nature. The debate has now shifted entirely to the mechanism responsible for this precision. When we strip away our philosophical biases and look strictly at the data, the scientific community is left grappling with three primary hypotheses to explain a universe that appears mathematically rigged for the emergence of complex observers. We must choose between a statistical miracle of unfathomable proportions, an infinite fractal architecture of unseen realities, or the existence of a deliberate, foundational blueprint. And as we begin to rigorously evaluate the mathematics behind the first hypothesis, the proposition that we simply won the ultimate cosmic lottery, we will uncover a statistical paradox that forces even the most hardened probability theorists to question the very nature of random chance. Evaluating this chance hypothesis requires us to treat the fundamental constants as independent, uncoordinated brute facts. In this framework, the parameters of the universe require no deeper teleological or theoretical justification. They possess the values they do simply because they must possess some value. From a strictly epistemological standpoint, this approach is mathematically parsimonious. It demands no exotic scalar fields, hidden dimensions, or external agents. It posits that asking why the cosmological constant is precisely calibrated is a category error, akin to asking why the integer 2 is an even number. The constants simply are what they are, and our existence is nothing more than an anthropic tautology. We observe a finely tuned universe because a chaotic, uncalibrated universe cannot produce biological entities capable of observation. However, the scientific viability of this brute fact framework collapses the moment we subject it to rigorous probabilistic modeling. When calculating the likelihood of multiple independent events occurring simultaneously, we must multiply their individual probabilities. We are not merely analyzing a single anomalous variable. We are looking at an intersecting matrix of at least 24 independent physical parameters, each possessing its own infinitesimally narrow life-permitting window. We must take the probability of the cosmological constant, 1 part in 10 to the power of 120, and multiply it by the precise strong nuclear force ratio. We must then multiply that product by the exact electromagnetic to gravitational force ratio, and multiply that again by the precise matter-antimatter asymmetry generated during baryogenesis. The resulting mathematical product plunges us into numerical depths that lose all physical meaning. To put this statistical impossibility into perspective, we must factor in the initial entropy of the universe at the exact moment of the Big Bang. The theoretical physicist Sir Roger Penrose calculated the required precision for the universe's initial low-entropy state to permit the formation of structure rather than immediate thermal equilibrium. The probability he derived is 1 part in 10, raised to the power of 10, raised to the power of 123. This is a double exponential figure so astronomically vast that if we were to write a 0 on every single proton, neutron, and electron in the entire observable universe, we would run out of subatomic particles long before we could write out the entire fraction. When we multiply Penrose's entropy parameter by the cosmological constant, and then by the specific resonances of carbon-12, the final probability approaches absolute zero so closely that statistical mechanics cannot distinguish it from utter impossibility. This staggering arithmetic is precisely why astrophysicists who dedicated their entire careers to defending a naturalistic model of the cosmos ultimately found themselves mathematically cornered. Fred Hoyle, who stubbornly resisted any model implying an external cause, was forced to concede that the chance hypothesis strained scientific credulity past the breaking point. The theoretical physicist Paul Davies has stated unequivocally that the extreme calibration in physics is a fundamental feature of reality demanding a rigorous explanatory mechanism. Calling it chance does not solve the arithmetic, it merely ignores it. Driven by the sheer mathematical absurdity of the chance hypothesis, theoretical physics pivoted toward a second, far more radical framework: the multiverse. If the existence of a single, isolated universe makes the extreme fine-tuning of physical constants a statistical impossibility, then the solution is to expand the probabilistic sample size to infinity. If there are countless universes, each generated with a randomized set of fundamental constants, then the anthropic principle ceases to be a mystery and becomes a statistical inevitability. In a vast ensemble of universes, the overwhelming majority would be sterile, chaotic voids. But given an infinite number of throws at the cosmic roulette wheel, a universe with our exact parameters is guaranteed to materialize eventually. We are simply inhabiting the statistical outlier. This theoretical architecture dissolves the fine-tuning paradox through brute force abundance. However, the multiverse is not a single unified theory. It is a broad categorization encompassing several distinct physical models. The equations of string theory yield an estimated 10 to the power of 500 possible topological configurations for hidden spatial dimensions, suggesting our universe is merely one localized realization within an incomprehensibly vast landscape. Inflationary cosmology proposes that quantum fluctuations in the early universe caused isolated regions of space to crystallize into bubble universes, generating an infinite fractal network of realities, each potentially cooling down with entirely different fundamental constants. The many worlds interpretation of quantum mechanics operates differently, positing that every quantum superposition physically realizes all possible outcomes in branching, orthogonal timelines. Over 14 billion years of continuous quantum decoherence, this mechanism would generate an infinite number of parallel realities. Beyond these, Max Tegmark's mathematical universe hypothesis suggests that every mathematically consistent structure must exist physically, while conformal cyclic cosmology models propose endless temporal iterations of big bangs and heat deaths. With enough universes, anything that is physically possible will exist somewhere, making the existence of our specific parameters completely statistically ordinary. Yet, for all its mathematical elegance, the multiverse framework extracts a devastating conceptual cost. It solves the problem of fine-tuning by multiplying the sheer volume of physical reality by an inconceivable, potentially infinite factor. To explain the precise calibration of one observable universe, this hypothesis demands the literal existence of trillions upon trillions of unobservable, dead universes. This introduces a severe epistemological crisis into the heart of the scientific method. The foundational pillar of empirical science is falsifiability. A hypothesis must make predictions that can be tested, measured, and potentially proven wrong. But by their very definition, these parallel universes exist outside our cosmological horizon, permanently causally disconnected from our reality. Prominent cosmologists, including George Ellis, have raised severe objections to this paradigm, arguing that invoking untestable realities crosses the strict boundary between empirical physics and metaphysical speculation. Ellis warns that the multiverse represents a dangerous kind of explanatory inflation, attempting to resolve a massive anomaly by introducing a theoretical construct inherently immune to empirical verification. If a theory can be adjusted to predict absolutely everything, then it fundamentally predicts nothing. In the pursuit of preserving a naturalistic explanation, physicists may have constructed the most expensive, untestable answer ever proposed, requiring us to abandon the requirement for observational evidence that made physics a rigorous discipline. This epistemological deadlock forces us to confront the third and undoubtedly the most controversial explanation for the extreme parameters of the cosmos, the hypothesis of design. This proposition suggests that the fundamental constants exhibit the exact mathematical signatures required for complex chemistry and biological observers, because they were purposefully calibrated to do so. It posits that at some foundational level of reality, a level that currently eludes our standard model of physics, an intentional agency or underlying teleological architecture dictated the initial boundary conditions of the universe. For a working physicist, articulating this hypothesis in a peer-reviewed context is deeply uncomfortable. It instinctively feels like a regression, a retreat from the rigorous mechanistic explanations of the Enlightenment back into the realm of supernatural fiat. To invoke an uncaused, unquantifiable intelligence as a variable in a physics equation appears to be the ultimate abandonment of the scientific enterprise. Yet, when confronted with the sheer, unapologetic precision of the cosmological constant, the carbon-12 resonance, and the matter-antimatter asymmetry, some of the most brilliant minds in theoretical physics have found themselves cautiously backing into this exact corner. Fred Hoyle's conclusion that a super-intellect had monkeyed with physics was the direct result of staring at the nuclear cross-sections of stellar nucleosynthesis. He is joined by an elite cohort of scientific thinkers who reached similar, highly guarded conclusions. The renowned astronomer Owen Gingerich, the esteemed British mathematical physicist John Polkinghorne, and the legendary theoretical physicist Freeman Dyson all independently analyzed the data and concluded that the universe exhibits the overwhelming appearance of having anticipated the arrival of conscious observers. They recognized that the mathematical architecture of reality looks highly engineered. However, the scientific cost of accepting the design hypothesis is arguably just as catastrophic as the untestability of the multiverse. If we attribute the precise value of the electron's charge, or the expansion rate of the vacuum, to the intentional choices of an unidentified designer, we are no longer dealing with physical facts. Intentionality cannot be quantified by tensor calculus. A designer's motives cannot be modeled mathematically. The design hypothesis provides absolutely no mechanical explanation for how the constants were set, it predicts no new physical phenomena, and it generates no testable data. In the strict epistemological framework of the scientific method, invoking design is viewed as a sophisticated placeholder for ignorance. It relabels the mystery without solving it. Substituting a physical anomaly with a metaphysical absolute, we are left trapped in an excruciating theoretical trilemma, where every available exit from the fine-tuning paradox demands an unacceptable intellectual sacrifice. Chance leaves us with an arithmetic probability so infinitesimally small that it insults the very foundation of statistical mechanics. The multiverse leaves us with a multiplication of reality to an inconceivable degree, demanding we accept an infinite matrix of hypothetical universes that permanently evades empirical observation. Design leaves us with an explanation that fundamentally breaks the rules of scientific inquiry, placing the ultimate answer outside the domain of physics entirely. The dials of the universe are turned with lethal precision, and the data remains unyielding, indifferent to our philosophical discomfort as we search for a mechanism that can explain why the cosmos is strictly engineered for our existence. When you hold these three mutually exclusive paradigms together, the mathematical absurdity of pure chance, the empirical impossibility of the multiverse, and the non-physicality of intelligent design, what becomes glaringly visible is an epistemological boundary. The mystery of fine-tuning does not behave like a standard problem in quantum mechanics or general relativity. It is not a missing subatomic particle waiting to be detected in a high-energy supercollider, nor is it a mathematical anomaly in a specific tensor field that can be smoothed out with a more refined gauge theory. It is a problem of a fundamentally different category, depending entirely on which of the three explanations you are willing to tolerate. The fine-tuning paradox either forces physics to become infinitely larger, forces it to become infinitely deeper, or forces us to concede that we have crossed into a domain where the methodology of physics simply no longer applies. We are attempting to use the internal thermodynamic and quantum mechanical laws of the system to explain the external calibration of the system itself. Theoretical physics is exquisitely equipped to model the interactions of mass and energy once the parameters are set within a Lagrangian framework, but it possesses no mathematical formalism to explain why the initial boundary conditions and fundamental constants were assigned those precise numerical values in the first place. the most intellectually honest position, and the one that the majority of thoughtful physicists privately occupy when the equations are set aside, is an admission of profound ignorance. We do not know. We do not know which of the three explanations maps onto objective reality. We do not know whether some fourth theoretical framework, a concept entirely unconceived by current human intelligence, will eventually emerge to dissolve the paradox. There is a non-zero probability that the question itself is mathematically malformed. It is entirely possible that our current confusion regarding the cosmological constant and the fundamental forces is a temporary cognitive misunderstanding, one that will look as primitive and strange to scientists a century from now as the ancient question of what physical object holds the Earth up looks to us today. Perhaps a future synthesis of quantum gravity, whether through an advanced iteration of string theory, loop quantum gravity, or a completely novel paradigm, will reveal that the constants could not possibly have taken any other values. Perhaps they are locked into their current configuration by some inescapable mathematical necessity, a topological inevitability that we simply cannot yet perceive because our mathematics is incomplete. But until that hypothetical unified theory arrives, we are tethered to the empirical data we actually possess. And what the empirical data demonstrates with ruthless consistency across every discipline of the physical sciences is that the universe we inhabit is exquisitely and precariously tuned. This is not a localized phenomenon or a statistical artifact. The calibration extends across 30 orders of magnitude, connecting the most macroscopic structures of the cosmos to the most microscopic biological mechanisms. It begins with the precise rate at which the vacuum of empty space expands, driven by a cosmological constant that avoids tearing galaxies apart in a big rip, or crushing them into a premature singularity by a margin of 1 part in 10 to the power of 120. It continues through the exact strength of the strong nuclear force, calibrated to bind protons and neutrons together just tightly enough to prevent the universe from remaining a sterile ocean of pure hydrogen, yet loosely enough to allow stars to act as gradual, stable fusion reactors over billions of years. It threads through the intricate quantum chemistry that permits carbon-12 to possess the exact resonance required for its synthesis inside stellar cores, ensuring that the periodic table can support complex molecular bonding. It weaves through the incomprehensible matter-antimatter asymmetry, the 1 in a billion statistical survival of baryonic matter that allowed anything physical to persist beyond the first microsecond of the Big Bang. The tuning does not stop at the edge of astrophysics or quantum chromodynamics. As the recent data from the experimental physicists at Queen Mary University of London demonstrated, the mathematical calibration descends directly into the physiological architecture of living organisms. The fundamental constants of nature, specifically the Planck constant and the elementary charge of the electron, strictly dictate the kinematic viscosity of fluids. Because these constants sit exactly where they do, within an impossibly restrictive numerical window, liquid water possesses the precise rheological properties necessary to act as a universal biological solvent. The viscosity of the liquid matrix moving through the cellular structures of the biological entities that are currently analyzing this data is governed by the same parameters that govern the ignition of supernovae. If the electromagnetic force were altered by a fraction of a percent, the fundamental equations governing fluid dynamics, such as the Navier-Stokes equations applied at the capillary level, would yield catastrophic biological results. The blood circulating through your vascular system right now would either become too dense to be pumped by a biological heart or too thin to maintain the osmotic pressures required for cellular metabolism. Every level of reality, every fundamental dial on the control panel of the cosmos, is turned to a value that explicitly permits the emergence of a localized system complex enough to build instruments, measure the dials, and notice that they have been deliberately turned. The British astrophysicist Fred Hoyle, who died in 2001 at the age of 86, recognized this inescapable pattern long before the modern consensus formed. Hoyle spent the final decades of his career engaging in fierce, often solitary battles against the prevailing orthodoxies of the scientific establishment. He argued relentlessly that the standard narrative of cosmic origins was fundamentally incomplete. From a purely historical perspective, he was demonstrably wrong about several major cosmological models. He famously refused to accept the Big Bang Theory, stubbornly clinging to the steady-state model, even after the discovery of the cosmic microwave background radiation provided overwhelming, irrefutable evidence for an expanding, temporally finite universe. He also championed highly controversial and ultimately unsupported mechanisms for the origin of life, such as panspermia, which largely failed to hold up under rigorous biochemical scrutiny. But regarding the central architectural mystery of the universe, Hoyle was absolutely right. And he was right decades earlier than almost anyone else in the theoretical physics community. He looked at the thermonuclear kinetics of stellar interiors and saw that the universe contains mathematical coincidences that simply do not behave like coincidences. He realized that the degree of precision required to permit the existence of atomic complexity is vastly greater than any rational definition of statistical luck can absorb. Half a century before modern fluid dynamicists proved that fine-tuning extends all the way down to the thermodynamic flow of blood inside living bodies, Hoyle understood that something fundamental about the structural integrity of the cosmos appeared to be set up in advance. He calculated the carbon-12 resonance and recognized that the parameters of reality were not arbitrary, but strictly optimized. We still do not know what set up that optimization. We do not know if the concept of a setting mechanism even applies to the fundamental nature of spacetime. We are left standing before a measurement that defies all physical intuition. We have the cosmological constant, a parameter governing the energy density of the vacuum, fine-tuned to a precision of 1 part in 10, followed by 120 zeros. To put that number into perspective, it is a precision far greater than taking a single proton, hiding it somewhere within the entire observable universe, and then blindly picking that exact proton on your very first attempt. We have a physical universe that exists exclusively because that measurement landed exactly where it did. And we have, sitting inside that precisely balanced universe, biological organisms whose internal fluids circulate through their bodies, because the very same quantum constants that permit galaxies to coalesce out of primordial gas also permit the correct thermodynamic viscosity for liquids operating. Inside organic cells, the universe is here, you are here, and the immutable laws of physics that allowed for both to exist sit precisely inside the